a particular lecture looks at probability, but in probability, we are starting from our module of biostatistics. And in biostatistics, I'm very sure in your previous interactions, you've been able to discuss what biostatistics is. Therefore, we want to just look at a certain part of biostatistics, which mainly looks at probability in this particular lecture. However, we are having particular objectives for this particular lecture here. And I was saying that after this particular lecture, we expect that as a student, you should be able to define probability, but also you should be able to understand some of the basic properties of probability. You should be able to understand some of the different measures or methods of probability. You should be able to calculate the probability of simple and compound events using the different formulas and rules. But you should be able to apply, most importantly, the concepts of probability to the real world situation. So if you're a demographer, you should be able to apply probability in your real aspect of demography. If you're a public health expert, or scientist, or you're a nutritional dietist, or you are an environmental scientist, and so forth, in your own particular field of study, you should be able to understand this particular probability, but also how you should be able to implement it in those particular aspects of in the various aspects in which all of you might attest to. So we want to understand the introductory part of probability by trying to figure out what we understand by probability. And in this case, we're saying that probability is about figuring out the chances of something happening, ranging from what we call impossible, which is a zero, to a certain what we call one. And we're saying that probability helps us make sense of these uncertain situations and make better decisions. So just imagine you have a group of about 10,000 people and you want to select 10% of them randomly. So the question would be that what is the probability that any of the 10,000 individuals can be selected? So in other words, you're making inferences, or you're making you're trying to understand, or you're trying to figure out what the chance might be for an individual to be selected among the 10% from the 10,000 people that you have. So probability uh, a probability of zero, like we said, a zero would imply that the event will never happen, and a probability of one would imply that the event is certain to happen. So, in other words, for any event that has probability zero, it would mean that uh, that event will not happen. For example, having the sun at the night hour, that is a probability that will never happen. Meaning, there is no way we can have the sun during the night, and during the day we have a different thing. So, whereas one implies that the event is certain to happen, meaning that it is going to happen. You're very sure that the event will certainly happen. But again, we're saying that usually these events that have probability zero or one are not very interesting to discuss. So you cannot discuss the outcome of something that you are sure about. You cannot discuss the fact that something will not happen. The discussion will become a little monotonous, and at the end, it is a very boring discussion. But also, similarly, you cannot actually have a discussion on an issue where you know the result is going to be one. Hmm? So, for example, if you do not do a paper, you know that you're not going to have results. So that end is already determined. So you cannot discuss modalities of how you may not be able to do a paper, but at the same time that you might have opportunity to have marks. So that discussion may not be able to yield in that aspect. So the notion P, where we are referring to as parentness, the notation that we're saying here as P with something in parenthesis after, such as we're saying the probability of A. So P is used to represent the probability of A happening. So in any regard, you can be able to write probability of A, where P is our parenthesis. And in that parenthesis, like we said earlier in our definition of probability, we are trying to figure out the chances or the chance that something will happen. So that is why we're saying that in that reference, we're saying the parenthesis A would mean to represent the probability of A occurring. So there are different descriptive notations that we can actually use. For example, we can say the probability of people having diabetes. So in your own field of discussion, when you want to understand the population structure or you want to understand some of the issues affecting your society in terms of probability, James, kindly mute. If you have a question, you can raise up your hand and we shall be able to pick. Kindly mute. Thank you. Yes. If you have a question, you can actually ask it. But I'm just doing an introduction of this particular lecture on probability. And you got when we haven't gone very far. If you're able to get the video recording, you will understand that I am just trying to start to explain the definition of I'm just trying to start to discuss the definition of probability in there. And so we're saying that when you're starting to use these descriptive notations, you may choose to use a descriptive notation based on your event of interest. For example, if you wanted to understand the probability of under 5 death, in other words, you want to understand the mortality rate in the society. So you would be having data for all mortality in the society, but for you, your interest, your event of interest is mortality under 5. So your notation for the parenthesis here would be the probability of under 5 death. So that is just an explanation of P in brackets, the event of interest in there. So if we wish, or we can use letters to represent our. You can use this discrete of female, probability of under fives, probability of individuals who have diabetes, but also you can say probability of individuals who live in urban setting, depending on your event of interest. So there are mainly two ways to determine probabilities, and one is by considering the situation theoretically, such as games of chance. And then what is the chance? Well, just theoretical consideration. This is useful if it can be done, but we cannot possibly do this when we want to do something like estimate the prevalence of diabetes among the US population. In that case, we must use data to establish the desired probability empirically based upon our observational data. So in your first way or method of using theoretical, for example, in a football game, there will be a win, there will be a loss, there will be a draw. So theoretically, this is a game of chance. So in a game of chance, you can just use a theoretical decision and say this is going to be a win. What many people call as gambling is also a probability. It's an application of probability. But again, the second way of the application of probability, or how we can determine probability, is by using data that is already available. For example, if you wanted to estimate the prevalence of diabetes in the UK, then you should be able to use the population that is at risk. The population that is at risk vis-a-vis the cases of diabetes. So it means that you already have an observational data, that you already have data that you're basing on. For example, if you had let me use the case of malaria. If if your population that is susceptible to malaria, or that the population that let me just create here one slide so that I can be able to explain what I am saying uh, in terms of statistics there. So, in other words, if you wanted to estimate the prevalence of malaria in South Sudan, then you should be able to have. This is the second way you're not using a theoretical method in trying to determine probability. Here you're actually using you're using observational data. So to determine this prevalence on malaria, you should be having observational data on malaria. So if malaria cases in this month, in the month of October, were 400, 4,050 positive cases, you should be able to subject this particular figure of 400 malaria cases to the population that is vulnerable, possibly meaning in malaria, almost all the entire population is susceptible or can actually get malaria. So you could subject it to 10,000, or I mean to 10,000 of the population. So let's say you have 4,000 50 cases in the month of October, and then here you are with your population of 10,000. So you should be able to calculate this 4,050 and divide it by 10,000, and it should be able to give you the figure that can give you the probability. So you can be able to see what would be the probability that out of 10,000 people, the number of people who can get malaria. So that is the probability that we are explaining in this statement that is up here. That is up here. So now we want to look at some of the key terms When we are having looked at the definition of probability, we want to look at some of the key terms that are related to probability. Throughout this particular session, we may be able to mention some of the words. So it is very important that we understand some of these key terms. And one of the key terms is what we call random experiment. Now, this is an experiment that has a known set of possible outcomes, and it is called a random experiment if it cannot be predicted in advance which specific outcome will occur on a given execution of an experiment. So, for example, we are looking at tossing a dice, or we are looking at tossing a coin, or we're looking at card draws from a deck. So we're saying why we're calling it a random experiment. For example, a dice has about six sides, about six sides. So meaning the random experiment, the outcomes are from a dice, the outcome can be 1, the outcome can be 2, the outcome can be 3, the outcome can be 4, the outcome can be 5, and the outcome can be 6. So that means that in a random experiment, you would have to predict the chances or the possibility that one of the outcomes can come. And that's why we call it a random experiment, because you cannot definitely say that the outcome will be one. So it has a set of outcomes, a set of possible outcomes, and that makes it to become a random experiment. Two is the term outcome. The result of any random experiment is what we call an outcome. So we suppose that when you toss a coin, for example, you can either get a head or you can get a tail. So when you toss the coin, the head is the upper surface. So tossing a coin is a random experiment that results into an outcome that is called a head. So the outcome of a head becomes when you toss the coin, uh, which is a random experiment because it has a set of possible outcomes. When the outcome finally occurs, it is a head, and if it is either a head or a tail, and therefore those particular results of the experiment are what we are calling outcomes. Thirdly, another key statement is what we call sample space. So it is a set of all the possible outcomes for a random experiment. All the set, you should be able now to understand the statements. We're moving from a random experiment to an outcome, and we're now moving to a sample space. And all that combination of the outcomes from a random experiment is what we call a sample space. And we're saying that obtaining a head or a tail on tossing of a coin is possible. And therefore, the sample space for tossing a coin is either a head or a tail. So the head and the tail are the sample space for tossing a coin. And similarly, if you roll the dice, or if you roll the die, there are different outcomes. So we can either get 1, 2, 3, 4, 5, or 6. So therefore, the sample space for rolling a die is 1 to 5, or I mean to 6. The other key term is what we call equally likely outcomes. Now, events with the same theoretical probability or likelihood or occurring are referred to as equally likely events. For example, the relative occurrences of a head and a tail on tossing a coin for a very large number of tosses are equal. So head and tail are equally likely outcomes that make the tossing of a coin fair and unbiased if it's to decide between two options. So we are saying that a dice, I mean a coin, has equally likely outcomes because it has two outcomes. It is either a head or a tail. And therefore, whether you tossed it for 3 or 4 times, the chances that the outcomes will be equal are the same, because there are only two options. Apart from a dice where you could in one toss you can get a one, another toss you can get another one, another toss you can get a two, another toss three, four, five, and six. However, for equally likely outcomes, there are only two. Uh, there are only two outcomes. For example, in volleyball, there are only two outcomes. It's either a win or a loss. So this is what we call equally likely outcomes. So another key statement that we need to look at here is what we call an event. So in the case of a random experiment, an event is a set of possible outcomes at a specified condition. For example, when you roll a die and 4 is not obtained. This event is the random experiment that is rolling of a die whose result is not 4. Therefore, this event has 5 possible outcomes that are 1, 2, 3, 5, and 6. So, suppose it's mentioned that event F is equal to obtaining a black card while drawing a card from a deck of 52 cards. In this case, event F has 26 possible
Okay.
outcomes. Someone has a question? Not. Okay. So in this case, the event F itself has 26 possible outcomes because there are 26 black cards, a total that is 13 spades and 12 and 12 clubs. So we are looking at the event that is going to occur. So like when we were defining a random experiment, the number of outcomes occur from an event that occurs. For example, throwing a dice is now an event that has occurred, and therefore the outcome occurs definitely when for example when we're saying here that the event is a random experiment that is rolling of a die whose result is not 4. So if the result if 4 is not obtained, then it means that the rest of the outcomes are very possible. So it will either be a 1, it would be a 2, or it will be a 3. And that is what we call an event, uh, an, a random experiment that occurs becomes an event in that regard. So we want to also look at what we call a statistical inference. In this bit of discussing probability, we want to use statistical inference as another key term in the art of probability. And we're saying that a statistical inference is like making educated guesses about the entire population based on what we see in our sample. So it involves sampling and so forth. So statistical inferences are very big. I'm sure you've covered it in part of your biostatistics lectures. Uh, but here we want to just understand in our context of probability how it happens. So probability forms the foundation of this process, and it is crucial for understanding the improving estimations. So what happens is that statistical inferences are just a process of using a sample to meaning that to make a decision, or it is like a hypothetical discretion. They help you make a decision on the properties of a population. Statistical procedures use sample data to estimate the characteristics of the whole population from which the sample was drawn. So you can be able to make statistical inferences and conclusions. You can be able to have a sampling, and then from that sampling, you're able to make conclusions on a wider population in regard to your observation. So scientists typically want to learn about a population. Now, when studying a phenomenon, for example, we want to look at the effect of a new medicine, uh, or we want to understand the public opinion, or we want to understand the results at a population level. For example, let's say we have the COVID vaccination that has been carried out in a particular population. Or per se, let us say there is a new dosage of anti-malarials that have been introduced in a population. So we want to understand what are the effects, or we want to understand what is the population's opinion, or we want to understand further what are the results of this new kind of medication at a population level. So it is much more valuable now than understanding only the comparatively few participants in the study. So in statistical inference, you can be able to project uh, from your sample what actually is the ideal outcome of this particular new medication. So how do we make statistical inferences? In its simple form, away from what you could have covered in one of your course units, deeply in statistical inferences, here we are saying that the simplest form of making a statistical preference or inference requires you to do the following. One is that you draw a sample that adequately represents the population. So this is where we are talking about in terms of probability. So if you're having 10,000 youth, uh, then you cannot sample 10 of them and you expect that you will come up with a conclusive statement that favors all the youth, or that is for all the youth. Two, you have to measure your variables of interest. What do you want to measure? You want to measure the effectiveness of disease. So, for example, if if you want to make a statistical inference on a new medication, say we have an anti-malaria, like I said before, so you should be able to estimate how from your sample study from your hospital. Let us say you want to understand uh, uh, medication from your new medication in this particular health facility. So you will look at how many malaria cases were there. Let us say we had 100 malaria cases. Now, that is your sample, 100 malaria cases. Now you want to know the outcome of this medication. How many of them were put on treatment, on that new treatment? So you can be able to estimate out of 100 people, if you picked 50 people who were tested positive for malaria and put under the new malaria treatment, and and 50, all the 50, the ones you sampled, 50 of them got healed or got the therapeutic right, then you can make a statistical inference out of that sample that is adequate. So the variable you're measuring there would be the effectiveness of the drug. So the third form is that you have to use a very appropriate statistical methodology to generalize your sample results to the population while accounting for sampling area. So you know that there is the sampling error, but here you have to use the statistical methodology that is right. We shall be looking at some of the statistical methodologies that you can use to actually do your sampling. But of course, that is just a very simple version of making statistical inferences, like I said earlier on. So, however, in the real world experience, you might need to form treatment and control groups and administer treatments and reduce other sources of variations. So, in your real scientific research, you may just have to create a control group, meaning that there's a group that you can give the treatment, then the other group you do not give them the treatment. So when you do the comparison, you can be able to assess the effectiveness of this new particular drug. So in more complex cases, you might even need to create a model of a process. There are many details in the process of making a statistical inference. So that is just the brief we want to discuss regarding statistical inferences. Let me just give you a little brief here on some of the common inferential methods. But I know, like I've said, you should have covered some of them in the different modules that you've covered. So the following are some of the standard procedures that you can use to make statistical inferences. One is what we call hypothesis testing, where you use a representative sample to assess two mutually exclusive hypotheses about a population. So statistically significant results suggest that the sample effect or the relationship exists in the population after accounting for the sampling error. So if your null hypothesis was that uh, long distances uh, do not actually contribute to maternal death. Then if you do your sampling and after your research study, you should be able to make and understand from your study whether there is a relationship between long distance and maternal mortality, and therefore you conclusively make a decision and state whether your null hypothesis is right or it is wrong. Another inferential method is what we call the confidence intervals, or what most people in mathematics call as the CI. So the range of values likely contain the population value. So this procedure evaluates the sampling error and adds a margin around the estimate, giving an idea of how wrong it might be. So most times you see the confidence interval, you can be able to see that at a confidence interval of 95%, whether there is significance in your area of study. So, for example, if you wanted to understand whether urban or place of residence is responsible for institutional delivery or for mothers to take contraception, you should after doing a confidence interval, it should be able to estimate for you whether place of residence is significant to contraceptive use. The third procedure or standard procedure you can use to make a statistical inference is what we call the margin of error. And here you are comparing similarly, it is close to using the confidence interval, but for it is usually for survey results. For example, if we did a population survey to establish how many people live in a particular area, then the margin of error, if it is calculated and it is negative zero, for example, negative 5% to positive 5%, then that margin of error is insignificant. However, if the margin of error is above 5% and negative 5%, then it is very significant and it would mean that there is a particular problem somewhere. Last procedure is what we call the regression modeling. And in regression modeling, we're saying it's an estimate of the process that generates the outcomes in the population. So in regression modeling, you're actually trying to understand the odds. For example, if the odd is 2, it can be able to define for you if you wanted to understand contraceptive uptake among using sex, for example, among male and female, you should be able to understand if the regressional value odd is 2, you should be able to understand that the odd of females using contraceptives is twice, so meaning that the chances of a female using a contraceptive is twice a male. Or if you wanted to understand whether the level of education affects contraceptive uptake, then using the regressional modeling, you can be able to generate the outcome. Odd one would mean that odd one against zero would mean that women who are, or male or people who are educated are less likely to use uh, uh, a particular contraceptive more than the others that are not. So this is how you, likewise, you can apply this inferential in trying to understand the demography of the population. You can help it to understand the chances of susceptibility to a particular disease. For example, if you did a regressional modeling on malaria death, then you should be able to ascertain the risk at which either younger people or youth or children or elderly people can succumb to malaria. So we want to look at the approaches to probability. That was a hint or a brief into the aspect of statistical inferences. Now we want to go back and understand what are the approaches to probability in this case. And yes, Rose, your hand is up.
Yeah, I first wanted to know something. You talked about tossing a die. I would
Yes,
like
yes.
to know the significance of probability of about tossing a die. How is it significant in the field of reproductive health?
Okay. So what happens in that example of a dice, we are trying to show you the different outcomes that come that result from what we call tossing a dice, which is an event. For example, in reproductive health, there are different events that occur. For example, if there is a pregnancy, so in that the event in that case would be a pregnancy. And in our event of introducing probability, we are saying we're looking at a dice, and we are saying this dice has about 6 outcomes, and the outcomes are that when you roll this dice, you might either get a 1, or you might get a 2, a 3, or you might get a 5 or a 6. We also said that there is a possibility that you might toss not a dice, but you might toss a coin. And if you toss the coin, you will have 2 outcomes, either a head or a tail. So in reproductive health, for example, an event of pregnancy would mean there are different outcomes. One, there could be an outcome of a live birth, but like we said earlier, like I stated earlier, that there are some events that have one outcome. For example, if you do not do an exam, you do not expect results. Now, such studies, you may not be able to, such kind of events may only have one conclusion. So in this regard, if you had an outcome, an event of a pregnancy, now there are different outcomes that might occur. And in those outcomes, we are looking at a live birth. We're looking at a stillbirth. We're looking at a macerated birth. But also we're looking at an event of antenatal care. Now these are issues that are rising. So if we said there are two outcomes from a pregnancy, now as a reproductive health student, you should be able to understand from my population. For example, in a health facility, if I have 10 pregnant women, the outcome, what is the outcome of this pregnancy? Is it a live birth or it is not a live birth? Now, the skill that probability is going to probably offer you here is that you now have to put other factors into account. How many of the 10 mothers have attended 8 antenatal antenatal care services? How many of the 8 mothers are able to come and take TPT? How many of the 10 mothers are using preventive measures? Now, from that aspect there, you can be able to determine the probability that out of these 10 mothers, you may not have a complicated pregnancy among them. But also, you should be able to look at an aspect of contraceptive uptake. So in discussing the probability aspect, we're trying to empower you with with skills. One of trying to understand what are the chances of an outcome, but also we're trying to help you to have a skill of being able to determine or to be able to project the outcomes that may result from a particular event. I don't know if I've answered your question.
Yeah, actually, I've understood it now. We can continue.
Okay. So we want to look at the approaches to probability. And we are saying there are three relative approaches, and one is what we call the classical probability, two is relative frequency probability, and three is subjective probability. And if we are looking at classical probability, we're saying that classical probability is based on the assumption that all possible outcomes of an experiment are equally likely, and that the probability of an event is the ratio of favorable outcomes to the total number of outcomes. So, like there's an example here. We're saying that if we are, let us assume that there are 1,000 residents in a town and 5 of them received the flu vaccine. In that case, we can say the COVID vaccine. So using classical probability, we calculate that the probability of an individual receiving the flu vaccine, which is what we were calling parenthesis the, as P, the probability of receiving the flu vaccine is equals to the number of vaccine recipients divided by the total population. So in that case, the probability that someone received among, if you went and sampled in your population, out of 500 people, out of 1,000 people, you have data that 500 people received the flu vaccine. The probability that an individual received the flu vaccine will be the 500 people who received divided by the total population. And it will mean that the probability that you will get a person that received a flu vaccine is 0.5 is 0.5. So in that case, it is actually meaning that you might get someone that if we were to sample from the definition you're seeing here, that all possible outcomes. So in this case, there are two possible outcomes. The possible outcome is that you will get someone who has not received a flu vaccine, and you will get a person who has received a flu vaccine. So the probability is 0.5. So meaning you out of every two people, one person has received and the other has not. That is what classical probability is looking at. That the probability of getting a head and a tail are equal because there are only two outcomes. So this is an explanation of a classical probability here. What is the probability of getting a one from a dice? The probability is 1 out of 6 because there are six. There are six what? There are six sides. But also, what is the probability of either getting a one or getting a two? Because there are two. There are two. Because there are two what? Because there are two events here that are occurring, then the probability will be 2 out of 6 because you're having two sides. You either get a one or you get a two. So the probabilities are half in that regard. Meaning here you will get either a one or you will get a two. So here we are looking at the probability that you toss a three or you get a four, and the probability still remains the same for all the outcomes. However, for six tosses, the probability that you will get either one or two or three or four or five or six is one. So if you toss the dice like this, the probability that you will get any of the six figures is 1. You cannot have a 0. I don't know if that is clear. If you have any question on that particular aspect, you can ask. But I hope it is my explanation gives you the view of a classical probability. In other words, that in this and that having this in and the probability of over the so that is the regard to classical probability. So if you're looking at relative frequency probability, in relative frequency, we're looking at the probability that is based on the observation of past data or occurrences to develop probabilities for the future. And that is why we are calling it relative. Relative meaning it is looking at a period of time. We're looking at a particular period of time. So it is often used when we have a historical data that is available to make these estimates. For example, for researchers who have collected data on the incidence of a specific disease in a population over the past 5 years. So, for example, if you wanted to understand the probability that in the next month you will have women coming for antenatal for 8 antenatal visits, you have to look at your previous data. Out of the 1,000 pregnant women, how many of them came for antenatal care in the last year? Now, from that basis, you can be able to use that data. Out of 5,000 women who were pregnant, only 10 of them came for antenatal care. then you should be able to establish relatively the probability that in the next year you will have this number of antenatal visits. So, for example, we are saying here that out of 10,000 individuals who were studied, 300 of them developed the disease in the past 5 years. So using relative frequency probability, we shall calculate the probability of an individual developing the disease as, so if we want to know, out of 10,000 individuals, 300 people developed a particular disease, what is the probability that an individual will develop the disease? We shall say 3,300 divided by 10,000, meaning that is 0.03. So that is the probability, or that is the chance that an individual will get uh, that particular disease. For example, if you looked at the rate at which malaria, I mean COVID-19 was spreading in the developed countries, the probability kept increasing. So as cases kept on rising, as cases kept approaching millions, the probability that someone would get COVID-19 kept increasing, and definitely you were able to see how much or how many people were infected. And this is how what people call incidence rates, or what people call the susceptibility rate are calculated, because then you can be able to establish that from this particular aspect, these are the number of people that we expect might get this disease. If we have already if we already have two infections of Ebola here, using probability, you can be able to establish how many more infections you will be able to have. And the last approach is what we call the subjective judgment probability. And subjective judgment probability is what was developed by the probabilist. The probabilist is someone who develops an idea on probability. And it was developed by D. Finetti, and it is the most intuitive definition of probability. Intuitive meaning it is cognitive, that you're making a theoretic judgment. Indeed, according to this approach, this subjective judgment approach, the probability of an event is the degree of belief, meaning it is a personal attitude. What is the belief of an individual? So in the approach of subjective judgment, we are saying that it is the degree of belief of a person. So the belief a person attaches to an event based on his or her available information. This reasoning holds only under the assumption of rationality, which assumes the people act coherently. So this particular approach only looks at what is the belief of the person, but the belief of the person is not independent. It is based on the events or the information that the person has. So, for example, what would be the probability of an individual getting pregnant? Now, this degree of belief is from the person, and it is based on the available information to the person. So if the person knows that they had a particular intercourse, then they should be able to have a higher degree that they have conceived. But also similarly, subjective judgment applies to contraceptive uptake. What is the probability that someone you do contraceptive counseling will take this particular kind of contraception. If you went and you're offering counseling on a method of contraception, you should be able to understand uh, that what information is available to this person, but also what is the level of belief of this person. Then from there, you're able to understand the subjective probability that this person may take this particular kind of contraceptive. Now, let's provide a more specific definition here. Imagine a lottery where you can win an amount of money equal to S if event E occurs. So here we are saying that if you win, you can win S if E occurs. If this team wins, you will earn 60,000. Now, to participate, you have to buy one ticket. Now, which is the price you would be willing to pay to participate in the lottery? So, if you indicate the price as pi e comma s, meaning that if I pay the ticket and this team wins, I will get the S money. Now, the probability of event E is given by this figure, that the probability that E will occur will equals to pi if I pay and E occurs, then I will earn this money divided by the money earned. Now that is a direct explanation of the subjective probability. But also we have another example here on subjective judgment. That imagine you want to predict the probability that your favorite football team will win the match tomorrow. You have the possibility to participate in a lottery where if the team wins, you obtain a prize of 1,000 euros. Otherwise, you gain nothing. So, the price here, which is the price you would be willing to pay to participate. So, let's say you are very confident about your team capabilities and you're willing to pay 700 euros. Hence, the probability your team wins the match tomorrow will be calculated by the probability of your team winning tomorrow will be if your team wins the pie, the pie is the pie is the constructive assumption there that if your team wins, you will be able to earn $1,000. I mean euros. You divide it by 1,000. You see, then you can be able to see that your figure is 0.7. So the subjective judgment there would be that my team is going to win. However, if you offer the lesser value, for example, the price you're willing to pay, if the price you're willing to pay is is less than this figure, then subjectively you already know that this person is is not going to the probability that the team is going to win is going to be less. Similarly, it also occurs when people go to the market to buy certain goods. When they see the quality of a particular, the price they are paying for something is not right, then they reduce the money that they are going to pay. For example, if you wanted to go and buy a utensil or a phone in the market, and then they told you that the price you should pay for this, okay, the price of this phone is $10,000. Then uh, you look at the phone and you feel it is not the quality that you would want. Now the price you're willing to pay will reduce, and definitely the probability that you will buy the phone lessen. However, if you realize that the phone is actually a very good one, but you may not be able to raise the $10,000. You will push your price that you're willing to pay to about 9,000 or to about 8,000, and that will mean that the probability that you could buy the phone are higher. So up to that far, I'm thinking that I'm going to end with subjective judgment because we're already an hour, and I will just conclude these other slides tomorrow. So to conclude subjective judgment, we have just said here that subjective judgment probability relies on personal judgment. It also relies on expert opinions or available information to estimate probabilities. It is used when historical data may be lacking and experts or stakeholders need to provide their inputs. For example, experts are assessing the efficacy of a new vaccine for a specific disease. It is subjective and may vary based on the opinion of different experts. It may not always provide precise estimates, and the accuracy depends on the expertise and the information that is available. So the same apply to COVID. The assessment on the efficacy of the vaccine depends on subjective judgment. For example, if you're using AstraZeneca, if you're using JJ, they are all on subjective judgment, and therefore the probability that someone who used AstraZeneca uh, uh, or used the Johnson and Johnson or used the Pfizer to be able to assess the efficacy of the three new vaccines would be based on a subjective judgment. Someone who used AstraZeneca will subjectively say that my two doses were able to protect me effectively, and I feel the vaccine is very important. Whereas someone who uses JJ would subjectively again give information that it works very well. Likewise, the experts who make JJ vis-a-vis the ones who make AstraZeneca would be able to give information about their own vaccines, and that would mean that the expertise or the information that they have given would change the opinions or the probability of someone taking a particular kind of vaccination. So, up to that far, do we have any questions so that tomorrow we can look at basic probability notation and other things and summarize this particular probability aspect? So, up to that far, do we have any questions? If we do not have any questions,